Let's have a look at programming of microcontrollers in C. Now before I continue with this, I'm assuming that you are familiar with the videos that I've done in terms of programming in CH, and that gives a good overview in terms of programming in C. I'm assuming that you've looked at the video series of programming Arduinos using CH. That will give you a good indication of how we interact with things for inputs and outputs, reading analog values, outputting PWM values, and sort of a basic circuit configuration in terms of how to have inputs and outputs of things. So with that background knowledge, even though we're not going to be doing the programming in CH, or we're not going to necessarily be using the Arduino library, but we're actually going to be controlling the microcontroller directly, that would give you a good understanding of how to approach things and get things done. Okay, so I'm also going to mention over here that a lot of the things that I am explaining is using the very basic principles. I know that there are some more advanced ways of doing things. It might be shortcuts of doing things. You do get people that like to show off and have fancy ways of presenting code. And what I found is sometimes keeping things simplistic and basic, even though it might be a little bit lengthier to type out, it usually is the way how things would, that you can almost guarantee that things would work. Making things complicated often is, and you try and find out where your error is in that complex line that you might have typed out. You can't find that error, and then you're spending hours sometimes trying to find or at least a typo that you've done that of a specific character, so that might be in a specific line, and you just can't find where it is that you made that error. So there are some of those, if I can call it, advanced programming code that will be in this document that we'll be working through, and I'm going to sort of indicate to you whether they are valid, or whether you would actually use them a lot or not. And I've actually highlighted them in red because it might be useful for you later on, but in terms of having to do your basic operations stuff, you do not need to really know them. Okay, so I'm just going to go quickly through also a breakdown in terms of programming C, just to give you again an overview and a bit of a refresher of what is needed and how you would go about with programming things. But I will go through it very quickly because, like I say, I'm assuming you've gone through those other videos before. Okay, so comments. So double forward slash allows you to comment anything that's after that, and the code will not be executed, or that text won't be executed. You can have a block of codes, which can be done with a forward slash asterisk and then end it off with the asterisk forward slash. So comments are quite useful to let other programmers know, and also yourself later on when you're trying to look at your own code, what you're trying to do and achieve in that specific code. We've got headers, and so headers are obviously the libraries that you're going to be using. There's like the standard input-output.h one that we've looked at. We're going to be also having delay.h library. So this is for the delay millisecond or delay microsecond function, should you want to use them. Then we've got our main program, which is indicated as int main void. Okay. Printing and output, you can use a printf command, which will be hello world. And you will realize also, now that we're busy using a microcontroller, you do not have necessarily a screen in front of you. A microcontroller, when we program these microcontrollers using CBAVR, the microcontroller is completely independent of the computer. We can disconnect the USB cable once the microcontroller is programmed, and it can operate as an independent thing. So it doesn't need to be connected to your computer as you had in CH. And so these printf statements can then often be used to output on a serial line as well. Okay, so integers, declaring variables as integers would be with the int statement. So you can have int x comma y comma z, or you can have int x equal to 0 comma y is equal to 4 and comma z is equal to 3. So those will all be indicated as integers, and it will assign to each variable a specific value. You can also have just this one line of int x comma y comma z, and in your main code you declare what those values of those variables are. So those are also ways that you can go about doing it. Keep in mind, whatever the expression is on the right hand side, that gets assigned to the value of x. So x over here is equal to whatever x it was plus 1, and that would be then stored in the value of x. Please, again, you read from the left hand side to the right hand side, so please note that it's not x plus 1 is equal to x. You can't have x plus 1 is equal to x as a statement, because whatever value or whatever the calculation is always stored on the left hand side of the equal sign. Okay, so you cannot have an expression on the left hand side. Outputting information, so we could say, for example, x plus y times z is equal to some value, and that would be, whenever there's a percentage d, that would consider it as a decimal or integer value, and so after the first comma, that would have whatever that expression is equal to will be stored over there, or appear where the percentage d is. You can also have x colon percentage d, y colon percentage d, z colon percentage d as an output. And so when the first percentage d appears, it looks after the first comma, sees there's an x, and whatever the value of x is will appear over there. You could have y then, after y colon, there's another percentage d, and look at the second variable after this expression. So it would be after the second comma, which is a value of y, that value will be then appearing where that percentage is, and the same is for z over there. So this is what the output would be when you type that out. The while loop, so while a certain condition happens, and a bunch of statements below that. Keep in mind with the microcontroller, because it's running so fast and at such high speeds, 16 megahertz is 16 million instructions being executed essentially within a second. So it's very high speeds, and so while 1 would allow this all to be repeated in your main loop, because you want to have these statements repeated so that if you missed one of those steps in between, hopefully when you push a button it will recognize and it will then execute a certain command. So a while statement, or at least a while 1 statement, is used always, and then you can also have while a condition, and then is true, then you can have some statements to follow. There is a do while loop. This format of the while loop, yes, it does work, I'm not disagreeing with it, but since I do find that often this way of the while loop being executed, a lot of people do create errors. So that's the reason I'm not even going to cover that over here. Knowing the normal while statement is sufficient. Your for loop. So for the initial condition of I is indicated over there. I must be less than or equal to 10. That's the condition is going to be checking all the time. And every time is going to increment I by 1. And then a list of statements will be executed. Keep in mind, semicolons are important over there, not commas. Okay, declaring of variables. So characters will be declared with char, integers with int, floating numbers with float, double numbers with double. Keep in mind that the evaluation version of CVAVR does not allow you to use double, but it does allow you to use float for floating numbers. Double is just an extension or a larger number of float, and as a matter of fact, using floating numbers is sufficient. Okay, so you can also add the following before declaration of variables. So you could have, for example, short int and then your variable name, let's say SI. And that will give you a short integer. You can have long integers, you can have signed and unsigned integers. Again, these specific values and what they will be, look at the help files for more details about that. I'm not going to go into detail with that, but be aware of that. Variables can contain characters, numeric numbers, and underscores. Do not start variables with underscores, as this can be defined constants used within C. So just keep that in mind when working with variables. Okay, assigning different base numbers to a variable. So, for example, over here, an octal number of 56 can be assigned to A, and that's done with A is equal to 056. So 0 would give you indication it's an octal number. I'll be honest with you, and that's the reason it's in red over here, not used often, so you'll find that the hexadecimal numbers and binary numbers are used more often. So over here, if you look at the hexadecimal number, FF is a hexadecimal number and it's preceding with 0x. So that 0x indicates it's the hexadecimal number that's about to follow, and that will store that value into B. Also, you could assign a binary number. So if you want to type out all the ones and zeros, you can do that. You just start off with a 0B, and we'll know that that is a binary number to follow, and that will store whatever that value is to C. Alright, escape characters. Escape characters are one that you probably will be familiar with is for a new line, and that can be useful if you need to have new lines on the screen. Because we're working with microcontrollers, you do not really have to have new lines outputted, and so that's the reason I've just made all this in red. These are things that are probably useful in normal programming of where you've got a screen as an output, but in terms of a microcontroller, you would hardly use these specific escape characters. Okay, then we've got the arrays. Okay, so again, you can have an array of integers. So I would be an array of integers consisting of 3 elements. ST could be an array of characters consisting of 30 elements, and you can assign a string in that when you declare it as an array. Okay, so the rest of the elements are 0 after this Y, or at least no characters. You can also have, let's say, integer of V, and then that would be with 10 elements in it, and all the elements will be assigned a value of 0. And then you could also have V2, for example, which would be an array of 10 elements of integers, and these would be the values that would be assigned to the first 5 elements of that array. Okay, other variable declarations, you can use the hash define, you can use the enum. Again, these are often used, the enum especially is often used more maybe in your normal code. There's been a couple of cases of using enum and this hash define on microcontrollers, but there are some issues that can come up with it. Things not often used, so something I'm not even going to cover over here. You can also have classes. So, for example, a user with a certain staff number and maybe a certain name or so. Again, structures you hardly use in microcontrollers because you've got so limited amount of memory. You're not going to try and consume memory with structures necessarily. Something just is appearing over here for your information, but it's not often used, or at least I haven't used it often. Arithmetic operators, so you've got your addition, subtraction, multiplication, division, and modulus. Modulus operator does not work with the float, double, and long double variables. Okay, so keep in mind modulus, that is like, for example, if you say, what is 17 modulus 2? Or it would be 17, what is 17 divided by 2? Well, essentially that is 2, and what's the remainder is 1. So 17 modulus 2 is an answer of 1. Okay, so it's the remainder value that you're looking at. You can also say x is equal to x plus 1. You can have also x plus equal 1. You can have x plus plus or plus plus x. They add 1 to the value of x. It's just a difference in terms of whether the addition happens and is stored into x in different sort of orientations and stuff. But when it comes to programming with microcontrollers, we often just say x equal to x plus 1 or x plus plus. That's, and you've seen a for loop as well. I plus plus gets used quite often. So that is more common ones that are used. Logical operators, we've got less than equal to, greater than or equal to. Remember this when you do your comparisons with your if commands. You've got equal to, remember it's double equals. You've got not equal to, that's exclamation equals. So again, for your if commands, you've got your or statements and your and conditions that you can include in your conditions. And so these logical operators are used a lot. You also got your bitwise operators, so your bitwise and bitwise or and bitwise exclusive or. So that is if you want specifically one bit at a time to be manipulated. We'll look at an example below here in a few seconds. You've got your right shift and your left shift. To be honest, these I have not used that often using with microcontrollers. I think the one time I did try and use it was in terms of having like a Knight Rider type of effect of lights going up and down. And yeah, I could have done, I got it working using that. And then, but then I also had a means of just doubling the value, because with binary numbers, if you look at the different columns of each bit, is essentially double of the previous one. So I just multiplied by 2 and that was, or divide by 2, and that was an easier way of doing it. So that's the reason I've just put in red. I'm not really going to be looking at that. You also got once complement, which is with that squiggly line if you need to invert all the things. So again, let's have a look over here. So over here we've got the bitwise operation. So z is equal to z and not 15. So essentially 15 is equal to 1111. So that complement inverts that whole number, so it becomes 11110000, and then each of those bits are then ANDed with each bit for the value of z. Over here we've got again this this bitwise operation, which is a bitwise exclusive OR. Okay, so this will toggle all the bits within the value of w except the first and second bit, and that's because of that 3. So that 3 over there represents the first 2 bits. Remember, when we're working with binary, the first 2 bits would be from the right hand side reading. So like in that number over there, that would be those 2 bits over there. So those are not toggled, but the rest are toggled. Alright, we've got our if condition. So if some condition is true, perform a statement. Otherwise or else, if that condition is not true, the default would be statement 2 being executed. You can also add this if condition in this way. Again, I'm not even going through that. I have seen people make errors with that, so I'm not even going to cover that. It's easier just to keep it simplistic. Okay, you could also have if a condition is true, then do statement 1, otherwise or else. If condition 2 is true, do statement 3, and if all these conditions are not true, go to the default else and do statement 4. Switch case expression is more of a table format in terms of the if statement. Again, something I've highlighted in red over here because I've seen a lot of people try to use this case expression or the switch case expression, and it's very dependent in terms of how you type certain things out. So over here, for example, A needs to be in apostrophes. Sometimes it gets put into double apostrophes. Sometimes it's there's just so many different ways that it can be done with the typo, and then people don't understand why it's not working. So that's why with the if statements it's probably easier to, because you've got more than a single expression you normally have to execute. And so that's something I don't even cover in the case over here though, because you don't hardly going to use the switch case expression. We've got functions. Okay, so again, you can have an int square, int x. So that int x would be the value that you're going to read into the function, and then you're going to have a return statement, which will say, in this case, say x times x. Calculate that, and it will return it to the function square. So in your main program, you can say the number squared is %d, and it can essentially be, could have been a number that the user has entered in, stored in num. And so you just say square num, that num value gets replaced with the value of x over there. It does a multiplication and it returns the answer to be placed over there. You could also use the hash define command. Again, I'm not even covering that because I've seen too many people make mistakes with that. Other useful functions to consider. So we do have over here string.h, that gets often used, ctype.h for certain tests with you might want to do with characters. Again, it's one of those libraries that I wouldn't hardly use if possible. There's ways of doing it using your own code. I have seen often where these character type functions are tried to be executed. Microcontrollers do not execute it correctly because of memory issues or so. And then again, you spend hours trying to figure out why things are not working. Math.h libraries for mathematical functions. Again, they're quite useful, but sometimes you actually have to code your own functions using basic math procedures. For your standard lib.h function, and io.h function for your input and output. You do have a time.h function, which for the date and time. I put it in red because with microcontrollers you hardly use it again, because otherwise you've got to have an input form to enter in the date and the time. And even if you do have that, then you've got the other issue that you need to have a crystal, external crystal, which will be specifically for the timer, and this can cause issues as well and stuff. It's very, you need to calibrate that all up and stuff. I'm not saying this doesn't get used, it does get used for some applications, but in general, you don't need to really use it. Okay, then you've got sorting of arrays. I'm not even going to go through the code over here in detail, but essentially sometimes you do need to sort arrays in order, and so you get your bubble sort. And essentially you're just comparing different elements in an array and you're swapping them around, and that's what this main feature's doing over there. You get also your entry sort as shown over here. It also goes and looks at the different elements in an array, compares them and swaps them around as needed. You get your quick sort and shell sort, which uses very similar methods but just a little bit differently. And again, it compares your different elements in different arrangements, swaps them around, and then it creates the array to be then sorted. The thing is though is whichever one you use is fine. When it comes to program of microcontrollers, I have not really had to use any of these sorting algorithms. So again, I'm showing them to you so that you're familiar with them, but it's not something I'm going to go into detail because I have not seen them being used in that type of application. Okay, so now that we've looked at the basic programming of things, we recapped on a bit of a revision on programming in C. Let's look at some applications. Now these applications are things that you're going to see need to be put into your code. Again, as I mentioned before, with this video series, you might have to go back to some other videos and just go over them again. And as you've covered certain things in the future videos, those will make sense again, and then vice versa scenario as well. So there's a lot of things that we're going through over here in terms of, so just aware of the procedures, but you might have to just go back to a video and recap on things to sort of see how they correlate with each other. Okay, so often you might have an LCD display that's connected to your microcontroller. Fortunately, with CVAVR, it allows you to actually set which pins is going to be connected to which pins on the LCD, and it will output to those specific pins the different commands and pulses and stuff as needed. So that's where you're going to use the hash include lcd.h library. Okay, so to display a string on an LCD, you would have the function lcd underscore puts f hello world. If you want to output a character to the LCD, a character in terms of a variable, you will use the command lcd underscore put char and then the character C over here in brackets. Okay, so there's no function to output a numerical number. Okay, so a function similar to the example below has to be used, which makes use of the difference of the number in the ASCII table and the ASCII value for 0 and 48. If you want more detail in terms of how the ASCII table is and how to manipulate the numbers with the 0 and 48, have a look at the programming of strings video, which is in the programming of the CH video series. Okay, then you're going to have in your code, you're going to have a procedure which will be void lcd num open float num. So you'll create this procedure in your code. Essentially, you're going to have different columns. You're going to have hundreds, tens, units, 10,000s, which will be characters, and you will initially set them to 0. Okay. So what you're going to do is you're going to be looking at the number that you've entered, and you're going to have to check in which column it is in terms of hundreds, tens, units, and 10,000s. So in this specific piece of code, I'm assuming there's only one number after the decimal point, and there's only the maximum number you can get is essentially 1,000 essentially. So if the number is larger, well, at least it's less than 2,000 though. So if the number is larger than 1,000, it needs to output the character 1. Okay. And then therefore we're going to say num is equal to num minus 1,000. So that means that we don't need to look at the thousands column anymore. And then we're going to be looking at the hundreds column. Okay, so this would be now for a value if it's like 1,502. So now we need to look at that 5. Okay, so if the number is larger than 100, which could be the case because now we've basically said 1,502, we've subtracted 1,000 over there, so now we're left with 502. Okay, so if it's larger than 100, we've got this while loop, and every time what's going to be doing is that it's going to subtract 100 from this number, and it's going to increment a value 100, which is for this 100. So it's going to check, is it larger than 100? Yes, it is. It increments it, this 100 value, and it's going to subtract 100. So this will happen 5 times. Eventually, the 100 variable will have a value of 5 in it. Okay, so the LCD put character will output the number 5. But keep in mind it outputs that 5 must be added to 48 because this is looking at the ASCII value of 5. That's what this is going to represent if we just have the LCD put char command for that. So we need to add the 48 to replicate it with the actual numerical value of 5. Okay, then we're going to be checking, is it the number larger than 10? Well, with 1502 we don't have any of this, so it will eventually just output a 0, and the same procedure will happen as we've done over here at the above. And then we'll be looking at the units value, and the same procedure will happen, but it will output the units. Okay, so now the issue comes in, what about the decimal point? So we output on the LCD a decimal point, and then we check if the number is larger than 0.1. Okay, so keep in mind over here, the input number was a floating number over there. So that's the reason we're looking at decimal numbers as well. Okay, and again, a similar procedure we're going to be looking. Is the number larger than 0.1? If it is yes, increment the 10,000 value, and we're going to subtract this 0.1 every time. So we're able to get one single decimal point then after that decimal point we've put onto the screen. Okay, so you could have more decimal places if you wish, and you'll just do a very similar type of piece of code as we've done over there. Comes to your main program, you have again while 1 because you want this to repeat all the time. You'll go use LCD underscore go to XY to go to a specific XY coordinate point on the screen. That would be essentially in terms of characters, so that would be position 0 on the X axis, and position 1, which should be the first line of or line number 1 on from the top. LCD num is a function we've just created to output this, and that will essentially output the number 10.5. The rest of the numbers over there will be ignored. LCD go to XY, so we go to the next line essentially. LCD put char would put this down as a character, or will output these numbers over here as a fixed value. Okay, so that is sort of a very much of a breakdown for LCD output, or to an LCD screen if you want to use a microcontroller. Next one, we're looking at the serial communication. Okay, so when it comes to serial communication, you're going to CVAVR is able to generate code. Okay, and it allows you to have, at least if you have the full version, it allows you to then go and have an interrupt service routine, and will generate this code for you. If you are not able to have the full version and you only use an evaluation version, you could actually type out this code above over here. Essentially, we're looking at this / USART receiver interrupt service routine. Type that out. The lines of code below that, up to over here where it says insert your code here, which is not integrated in the wizard. So all this code gets normally generated by the wizard. If you use an evaluation version, you might have to type out this all on your own. Okay. Before that interrupt service routine, I do have I'm storing a flash, a constant value for a robot number 1. So in this specific application, it was a robot soccer robots we were programming, and we wanted to give commands to specific robots, and therefore we were able to identify if it's for that robot or not by giving different robots different numbers, different names. We've got our short integer for POS, which is equal to 0, RIC is equal to 0. I've got unsigned character arrays of size 22. So ARRC receive, and then I've got ARR as well. Okay, so the packet length is of 22 characters. And essentially, this code that the wizard then generates is going to store in the variable data whatever character is received at a specific time. Now what you want to do is every time a character is received, you want to store that into the next position of the array. And what I normally do is, whenever I've got a string of data that I'm receiving from, let's say, a computer or another Arduino board, is I start off the packet with a hash character. So whenever I get a hash character, I know that this is my initial character that I'm going to be reading, and therefore it allows me to reset the pos variable to 0. So that tells me that that's my first character I'm getting. And then in that array I'm going to be storing this data. So in this case it would be the hash, it would be stored in position 0. If the data that I receive is not equal to ASCII 35, so to ASCII 35 is going to refer to the exclamation mark. And what I normally do is my last character is an exclamation mark for a packet of data that I'm sending. So in this way I can do two things. I can check if I receive an exclamation mark and I'm expecting to receive, let's say, 22 characters. If pos is not equal to 22, it means that I've received a corrupt packet and I need to not react to the information I've received. At the same time, it allows me then also just to keep track in terms of where I am in that specific packet. Okay, so if the data is not an exclamation mark, it needs to increment the value of the position in the array and then store in that position the value of data. Okay. Now I'm going to verify if that packet was received. So first, if so what I'm doing over here is if data is equal to ASCII 33, okay, and the received packet that I'm getting in position 1, remember that with arrays we're going from position 0, is equal to the robot number, and pos is equal to 21. So remember, with an array of 22 elements, the biggest element position would be position 21, because we start off with position 0, sorry. Then I'm going to set this flag RSC is equal to 1. So I'm trying to indicate over here with this flag in the main program that I've received now a full packet and the main program must execute this code. Remember, as I mentioned before, that your serial data received is a lower interrupt compared to external interrupt procedures. So you want to minimize this code as much as possible so that your main code can then go, and even if your main code had to stop, at least it's able to go and execute certain commands and stuff, even if you get other external interrupts that might be executed in the background. So the first thing I do is I copy the array to an array to work from, because if you've got all these interruption of these external interrupts happening, you do not want to go and have this ARR underscore receive array maybe having more data now being inputted with hash and other numbers, and you're busy reading from that to maybe know what a specific motor speed needs to be. In the meantime, that value has been updated by a new value from that you've received, and therefore you're getting some corrupt information. So, as it could be a value that's even meant for another robot, it could be that's not meant even for this robot. Okay, so I want to copy everything. So if RC, or if receive, is equal to 1, first thing I need to do is I need to reset it to 0. So it allows me then to, in the future, to check if I need to, if I've received a new packet of information. Now I've got this for loop, which is going to go from 0 all the way to 21, and essentially is going to copy the value from each element of this RRR receive packet into the RRR array. Okay, so once I've done this, then in my main program I can start going and taking out each character, multiplying it together to get values, to be able to know, okay, well, maybe each character is representing a certain speed you want for a specific motor, and I can use that, and I can then adapt my code to follow those instructions. But it's important to always just first copy it across so that the array that you are busy doing calculations from doesn't get corrupt with new data that's being received. Okay, then let's also have a quick overview for analog to digital conversion. So the analog to digital converters is done with the read ADC or read underscore ADC command. Okay, so again, you're able to set with the wizard in terms of whether it's an 8-bit or 10-bit conversion, but usually we use a 10-bit conversion, so the maximum value is 1023. So as an integer, I'm going to have two variables. I'm going to say available 0 and available 1. That's what an aval, or that would be the analog value for 0 and analog value for 1. So that's what aval 0 and aval 1 refers to. So aval 0 is equal to read underscore ADC 0. So whatever value you read from that analog to digital conversion on pin 0 on ADC 0 will be stored in this variable aval 0. And then similarly, you're going to be using read underscore ADC 1. So the A to D conversion pin 1 value will be then taken and stored into this aval 1 variable. So it's quite easy to read and store, read from the analog to digital conversion stored into an integer variable. Timers. So I think before I continue with timers, let me go to a piece of paper and explain to you how timers operate in that manner. Because once you understand how the theory behind timers work, this will become then a little bit more clearer to you.
Let's have a look at timers. So with timers, you've got to consider it as being almost like a step ladder that you're going to be climbing. You've got a step ladder that you're going to have to climb up, but it's only once you get to the top ladder and you essentially fall over that you will be notified about it. So once you get to the top ladder and you fall over, you're going to get an injury and you're going to know about it, right? Okay, so essentially that is a very similar principle we're going to be keeping in mind when we're working with timers. Okay, so with this specific timer, we're going to be considering a 16-bit timer. Okay, so that would imply it's 2 to the power of 16. Okay, and that is equal to 65536. You can also use the 8-bit timer if you wish. Obviously it will be a smaller number, it will be up to 256, but the same principle will occur. Yet keep in mind with the 8-bit timer, you're probably going to have larger numbers that you need to take into account in terms of how many times this falling off of the ladder is going to need to happen. Okay, but for now, 16-bit timers is equal to 65536. Okay, so what is the time period, or T, okay, to climb a ladder? Oh, sorry, no E over there, to climb the ladder. Okay, every time the clock pulse is going to happen from the crystal, and it's going to pulse on the microcontroller, the microcontroller automatically goes and climbs one of these ladder steps. Okay, so we need to decide, well, if we're going to, for this specific scenario, we're going to be considering a crystal of 16 megahertz that we're actually using. Okay, so for us to climb one of these steps, that would be equal to 1 divided by 16 megahertz, or 16 times 10 to the 6. So that will allow us to get an indication of how long it's going to take in seconds for us to climb one of these steps. But how long is it going to take for us to climb the 65,536 steps? Because that's the amount of steps we've got, because it's a 16-bit timer. Okay, and so therefore it's going to be the time period it takes for one step to be climbed multiplied by 65536. Okay, and that's equal to 0.004096. Okay, so that's the first thing we need to keep in mind and calculate. Now we're going to have a look at what time period do we want to pass. So our timers are going to keep track of, let's say, every 100 milliseconds. Maybe every 100 milliseconds we want to see how fast it, or how many times feedback encoder from a motor has actually been giving us pulses, because we want to determine every 100 milliseconds how fast that motor's gone, and we want to correct it. Now when it comes to motors, especially when you want to do these timers, you're generally going to be looking at about 100 millisecond as a minimum anyway. You could push it down to 50 millisecond time periods if you wish. That is plausible. But sometimes what I have found is that if you've got a large piece of code, that code doesn't get time to run through a whole cycle within that time period. And sometimes it does then cause problems. So 100 millisecond is a good value to be doing it. So that would be around about 10 times a second it will be doing a check in terms of the speed. Okay, so 100 milliseconds is what we're going to be looking at. That's equal to 0.1 seconds. Okay, so how many times does this value, in terms of the number of falls that we're going to experience on this ladder, going to happen in 0.1 second? Okay, so in other words, how many times does 0.004096 go into 0.1? That will tell us how many times you've fallen off this ladder in a period of 0.1 second. Okay, for us to do that, we've got to then say, okay, 0.1 divided by 0.004096. Okay, and that's equal to 24.41 times. Okay, so within 0.1 second, we're going to be falling off this ladder 24 times. So that's great, but we want to get quite an accurate measurement in terms of 100 milliseconds. Well, it is difficult. These crystals that we are using, like the 16 megahertz crystal, it might not be exactly 16.0 megahertz. It might be 16.0529 megahertz, or it might be 16.00216 megahertz. It's not exactly 60 megahertz, so that time period interval is going to be a little bit off, but it's very close to 16 megahertz. Okay, so the thing is we know that it's going to happen in 24 times. Okay, so 24 cycles of falling off ladder is needed, okay, for this interval to happen. But what we need to take into account though is, oh yes, and by the way, so every time you fall off this ladder, yes, you get an injury, you realize that, but then you keep on climbing up the ladder from the start. So that's sort of the cycle that we are talking about. You climb this ladder from the beginning, because the initial value is 0, you fall down, you get to the bottom again, and you keep on climbing. Keep in mind, the only way that the microcontroller is able to notify us with these timer interrupts is every time you fall off the ladder. So it's whenever you get to the top of the ladder and it goes back to 0. Okay, so we've got that to happen, but the problem is that we've got now this 0.41 times or a fraction. It's basically a fraction of a cycle that needs to happen as well. Okay, now if you had to do this on a calculator, you'll see that there needs to be a 0.4140625 cycle too. So we also need to include this last cycle or fraction of a cycle that will happen. Okay, so to do this, we take this number and we see what fraction of that would be that of that 65536. So in other words, how many steps would it take for this fraction of a cycle to happen? Okay, so therefore 0.414065, and yes, I'm typing the full amount into the calculator because it's a high accuracy that we're able to then get. That multiplied by 65536 is equal to 27136. Okay, so therefore 27136 ladders must be climbed for that fraction at 0.41400625 times of that full cycle. Okay, so for fraction of cycle. Okay, now the issue is that that's great. We've got 65,536 steps over here to climb on this ladder. But now we're indicating that we need 27,136 steps to be climbed. It's actually steps, not ladders. That would be quite a lot of ladders to do. So 27,136 steps that must be climbed for that fraction of the cycle. Okay, so again, the only time that we know or any information we can get back from the timer is when we are falling off the ladder. That's the only information or time that we are notified something from the timer is when this falling off of the ladder happens, so we got to the top. So essentially we need to see how far from the top we're going to need to be for 27,136 steps to occur. Okay, so that means that we need to find a value x over here. X being the number of steps that we got to start off from and start climbing to get to the top for 27,136 steps to occur. Okay, so for us to do that, we say, okay, therefore 65,536, which is the number of steps in a total ladder, okay, minus this 27,136, which is the number of steps we've got to climb, is equal to 38,400. Okay, so we need to climb to step number 38,400 as our starting position to then go for every pulse and climb a step, and then we'll fall off for the final cycle, which will then be equivalent to 0.1 seconds. Okay, so again, just to go over this again, every time we fall off a ladder, we get injured and we sort of are made aware that we've fallen off a ladder. So we know that there's 65,536 steps on the ladder. Okay, so we need to then see for 100 milliseconds how many times we're going to have to do these steps, and we've calculated how long it takes to climb one step. Okay, so therefore for 0.1 seconds we divided by this time period that we've calculated for one step to be climbed, and we find that's 24.41 times. So that 24 over there we're going to now keep in memory. It's going to be important because we know it's 24 times that we've got to do. But it's 24 times and a bit. A 0.41400625 of a cycle that we need to climb to complete a full 0.1 second time period. Okay, so we take that 0.41400625, we multiply it by the number of steps, which is 65,536, and we get 27,136. Now we must see how far, for 27,136 to be a certain distance away from the top, or so many steps from the top, we need to see how many steps we're going to have in the beginning. So we need to, on the final cycle, almost fly up from the bottom. We need to fly up to the step number, a certain step, which should be step X, and then from there we will then continue climbing up the steps until we fall off. Okay, so to be able to know what that value of X is, we take 65,536, which is the number of steps in the ladder, minus that 27,136, and we're left with 38,400. Okay, and that's equal to X. Okay, so after falling off this ladder 24 times, we're going to then go fly up to position 38,400, and then we're going to start climbing a step every time a heartbeat or a pulse is received from the crystal, and then eventually we're going to fall off the ladder again. And once we fall off that ladder, then we're going to know a complete 100 millisecond has passed in that time period.
Now that we've had a look at how times operate in theory, let's now see how we would implement this in code. Okay, so we're going to be looking at the timer TCNT1, which is a 16-bit timer in a specific example. Okay, and every time this clock pulse of the crystal should be happening, it's going to increment the steps it's going to happen. Okay, and so eventually when an overflow happens, in other words, as soon as you fall off the ladder, then this interrupt is executed. Okay, so we need to now see how many times this interrupt is executed, and then we're going to change the initial value of TCNT1. Now normally we would assume TCNT1 to start off from position 0, because you'll be climbing from the ground up onto the ladder. Okay, so CVAVR's wizard will generate the code for these first two lines to be able to indicate to you where you've got to include your code, at least for the timer 1. Okay, so what's going to happen is every time I'm falling off the ladder, I want to take note of this and I want to record this. So that's where this t variable is, and every time I'm falling off the ladder, I'm going to increment the value of t. Now t is declared as a global variable before this, basically in the beginning of the code where some variables are declared. And so the reason is that normally with your local variables, if you had to exit a procedure, it would forget about the values stored in these variables that you might declare inside your procedure. So having it as a global variable will keep on recording in terms of what the previous value was, should that value have changed. Okay, so therefore t is going to be incremented and it's going to record that. Now, for this specific example, if I recall correctly, a 4 MHz timer was, or crystal was used, and we only want a 10 millisecond time period to occur. So these values are going to be different, but I'll tell you how the values that we've just calculated would then be replacing other values over here. Okay, so in this example, if t is equal to 12, it means that in the calculation we did for this is that for 10 milliseconds, 12 times interrupts have to happen. So there needs to be a 1 over there as well. And then one interrupt from a value of 0xb1cc. Okay, so essentially with this specific example, the calculations were done that 12 interrupts have to happen, and then you've got to fly up to ladder number B1cc to do the final fraction of the climb. Okay, so in terms of the example we've just looked at and that we've calculated, you would say, well, if t is equal to 24, because we found that 24 times is needed to fall off the ladder with a little bit of a fraction, and that fraction is that value that we calculated to be 38,400. Okay, so if t is equal to 12, or in our example that we looked at equals to 24 cycles, then it means that it needs to do that last little bit of fraction. Now, being a 16-bit timer, we do have the situation that the first 8 bits is considered as a high byte, and the last 8 bits is considered as a low byte. So for this B1CC, for example, we have to actually set the high byte to be 0xB1 to take into account the first 2 characters, and then the low byte of this timer is 0xCC to take into account those 2 times. So what we would have to do is that 38,400, we would have to take that and convert that into a hexadecimal number. Now you can do that quite easily using calculators. Most of your scientific calculators, especially the calculators that are even in Windows, allows your scientific mode to convert a decimal number to a hexadecimal number. So we can use that to be able to know what the first 2 characters and the last 2 characters of this hexadecimal number would be. Okay, so this is the starting position of our final cycle that we have to do if we had to start off from 38,400, and that would be replaced by 2 hexadecimal numbers, one for the higher section of the number, and then one for the lower 8 bits of the number. Okay, now any other time when we've got t that is not equal to it's not equal to 12. If t should be, let's say, less than 12, it's just going to increment t every time this interrupt happens, and all this rest of this code will be ignored. But now, obviously, once this final loop has happened, so in other words, on the 13th cycle in this example, and our example would be on the 25th cycle, so we can say that else if t is larger than or equal to 25 and RSC is equal to 0, then we need to reset the clock for 10 milliseconds. In other words, we need to start then climbing again back from the bottom of the ladder. So therefore, TCNT1H will be equal to 0x00, and TCNT1L would be equal to 0x00. So we're resetting this register to 0 again. But at the same time, every time this should happen, we need to then reset t equal to 0. So essentially, we know now 100 milliseconds or 0.1 second has passed, and therefore this t increment is going to keep on going and incrementing every time this overflow happens. But we don't need it to continue counting now from, let's say, 25, 26, 27. We need it to go from 0 again to be able to make sure that 100 milliseconds are going past every time. So therefore we need to make t back equal to 0 over here. Okay, so this code is sort of a standard code that you would almost be using to take into account this the time and intervals. Yet what would happen is you would find that this initial value of t that you're going to be comparing, that might change to whatever the amount of cycles is that you've got and calculated. So in the case that we did, it was 24. This will be the value that you would have of the ladder number that you're going to fly off for the last cycle, and before you actually climb the last bit of the ladder before you fall off. Over here, we're going to have t must be larger than or equal to the value that you've calculated plus 1. So in other words, for us it was 24 was the value that we calculated in terms of number of cycles, plus 1 would be 25, and then whenever that value should be reached, we're able to then go and set it to 0 everything over here. This RSC equal to 0 that's being checked over here, this is just to was probably a flag that I set in this specific code to check if a certain value might be equal to 0. So for example, if I'm checking every time if 100 milliseconds have gone past and stuff, I might want to include over here a line that says RSC is equal to 1. So in my main code, I can check, well, if RSC is equal to 1, then change RC equal to 0 again, and then count how many times we've had it that certain pulses have been received from the encoder, and therefore we're able to calculate speed and stuff, and that will allow this timer overflow then to start doing calculations from the start again. Okay, so we've covered over here very briefly, just to go through everything again. We've looked at the code in C, we've looked at the basic C commands and statements that you would do when programming any type of C programming, and then we started looking at, in terms of the application, we started looking at LCDs and LCD displays. Now you would output characters on the LCD display. Because we can't output numbers to the LCD display, we can only output characters to the LCD display. We then went and continued with serial communication, how to receive a one way at least to receive a data packet, how we can initiate it in terms of our initial character that we're receiving, how we can identify if the final character has been received, and then also after we've done that in our main code, we go and we copy the array into a new array that we're able to then use and read data from, and then use that data to control different motors or different outputs that we might have depending on the project that we're working. We looked at how to get values from an analog to digital converter, and then we also looked at timers. We looked at the theory behind the timers, and then how to implement those values that we've calculated in our code for a specific timer.